So hello student, in this lecture today we are trying to understand pulse laser deposition technique. Okay, it's a short form is PLD technique. So in short, this technique is called as PLD. It means it is a pulsed laser deposition method. Now you all are aware about laser. So this is a light amplification by stimulated emission of radiation. Okay, so this is a laser. Okay, so in this deposition technique, basically we are going to use laser pulses, okay, for the synthesis of thin film. Okay, how we can use it, that is what we are trying to understand in this lecture. So the pulse laser deposition is a physical vapor deposition technique. Okay, because in this technique again we are going to use vacuum. There is no liquid, there is no solutions we are going to use. Okay, so this is a physical vapor deposition technique, in which it means in this technique high power pulsed laser beam is focused inside a vacuum chamber to strike a target of the material that is to be deposited in the form of thin film. Okay, so in this technique, like we already discussed in the DC and RF magnetron sputtering, okay, there is a requirement of a chamber. Okay, so in this technique also we need to use a chamber. So in that chamber, what is there? There is a target and there is a substrate. Okay, so target holder holds the target and substrate holder holds the substrate. Okay, and in this situation, okay, a laser pulse which is kept, the laser source which is kept outside the chamber, it generates a pulse of laser, and that laser pulse we have to focus, okay, on target, on the surface of the target. Okay, so that this laser pulse will generate a plume. Okay, so what is plume? I will show you. Okay, so that is called as a plasma plume. Okay, and that is generated and the material is started to get deposit on the substrate. Okay, so that after sufficient number of pulses, okay, you will get sufficient thickness. Okay, now this material is vaporized from the target. Okay, when the laser pulse is get incident on the target, then what happens? Because it has a very high energy, okay, the material, the target material gets vaporized. Okay, and then it get deposit in the form of a thin film on the substrate. Okay, so this is the method, this is the technique basically, where we are using the laser pulses to evaporate the target material, and that evaporated target material get deposited on the substrate. Okay, so let us try to understand how the machine looks like and how it works. Okay, so in this figure, in the schematic figure, what you can see is there is a source of laser. A source of laser is available, you need it. Okay, without the laser pulses we cannot able to do the deposition. Okay, so we need a source of laser. Okay, then as you can see, there is a dome which is also called as a chamber. Okay, you can see there is a deposition chamber, and it has a window. It has a window, okay, where the laser pulse can pass inside. Okay, so through this window the laser pulse can pass inside the deposition chamber. Okay, so that window is of course transparent, and the remaining part of the deposition chamber will be prepared with the stainless steel or some kind of metal. Okay, so inside you can see that inside the chamber you can see that there is a target holder. There is a target holder, substrate holder is there. If you want, you can increase the temperature of the substrate in order to get a highly crystalline, good quality, okay, thin film. Okay, and you can see there is an oxygen inlet. Okay, so if you are depositing metal, then in that case you need not to use oxygen. Okay, but if you are basically trying to deposit some metal oxide, then it is better to use some oxygen gas. Okay, and as I said, when the laser pulse get incident on the surface of the target, there is a generation of plasma plume. Okay, there is a generation of plasma plume. So how this plasma plume looks like, so that you can see in the photograph shown on the left hand side of this PPT. Okay, so as you can see, okay, so the light which is coming out, okay, is basically target. Okay, and there is a plasma plume, okay, is generated because large number of laser pulses continuously get incident, okay, get bombarded on the target. Okay, so after sufficient repetition of pulses, there is a formation of plasma. Okay, and it has a kind of a structure which looks like a plume, so we call this as a plasma plume because it's a shape looks like a plume. Okay, so we call this as a plasma plume, and in that plasma plume, okay, there is a elements which are present in the target, and the same elements they started to get deposit on the substrate. Okay, so in front of this plasma plume you should have your substrate. Okay, so this is an arrangement where basically you are going to use plasma pulses, okay, to generate you are going to use the laser pulses to generate the plasma plume, and that plasma plume contains the elements which are present in the target, and these elements started to get deposit on the surface of the substrate. You can see that this is another pictorial representation of this PLD technique. This is the situation which is present inside the chamber. So what I am going to show you here is that with this kind of a technique you are easily able to prepare multi layers of different materials. So if you want a thin film, okay, where there is an alternative layer of zinc oxide and tin oxide, for example, so there is a 10 nanometer layer of zinc oxide, 50 nanometer layer of tin oxide, again 10 nanometer layer of zinc oxide. If you want such type of multi layers, okay, then it is possible to do with the help of PLD technique. Okay, how that you can see in this slide. So in the upper left picture, what you can see is that there is a deposition of target 1. For example, suppose there is a target 1 is available. As I said, it is a zinc oxide. Okay, let's assume. Then you can see that there is a shutter which is present on the target, as well as there is a shutter which is present on the substrate. Okay, so once you remove the shutter from the substrate, then your deposition, the material start to deposit on the substrate. Okay, so you can see that, okay, a laser pulse is coming and get bombarded on the target 1, and there is a formation of plasma plume. Okay, and that plasma plume is basically get deposited on the substrate. Okay, in the next picture on the upper right hand side of this slide, as you can see that, okay, suppose there is no shutter on the targets. Okay, there is a shutter on the target because we don't want the contamination of one target on the another target. Suppose we are depositing target 1, then some of the elements of target 1 may get deposited on target 2, target 3, target 4, target 5. Okay, so you can see here in the second image where at the max, okay, you can use here 6 different targets which are available. Okay, so you can fix all these targets at the same time. Okay, and as per the requirement, you can make the thin film of individual target, or if you want, then you can also make alternative thin films of 2 or 3 targets. Okay, so in the lowest picture, as you can see that when there is a target 2, then definitely, because target 2 is made up of some different material, then the color of plasma plume has got changed. Okay, and now you are getting some different color of that plasma plume. So just you can identify in picture 1 there is a target 1, and in the picture 3 there is a target 2. Okay, so this is the way, okay, where you are able to use one source of laser, and just by changing the position of the targets, okay, you are able to deposit your interest of material. Okay, so here in short we can try to understand, okay, how fast is this process to generate the plasma plume. Okay, so you can see there is a time evolution of the pulse laser deposition plasma plume. Okay, so you can see we have shown some schematic representation of these steps, what are happening with the surface of the target, okay, when the laser pulses are get incident. So as point 1, you can see the laser pulse, okay, with 20 nanosecond pulse width. Okay, so 20, after each 20 nanosecond there is a laser which get incident on the surface of the target. So these laser pulses basically hit the surface of the sample. Okay, so initial laser pulses, they get absorbed in the target. Okay, and once they get absorbed, then what happens, the surface of the sample started to become hot. Okay, once it become hot, then the pulses which are get incident on the surface of the target, okay, what it start to melt the initial layer of the initial surface of the target material. Okay, so the surface of the target start to melt. Okay, then what happens, continuously these pulses are get incident. Okay, then what happens, it evaporate in the form of a plasma plume. Then there is a formation of a plasma plume. And once the plasma plume is generated, okay, then what happens? This plasma plume contains the elements which are present in the contains the ions, okay, which are present in the target material, and these ions, they get deposited on the surface of the substrate. Okay, so then they resolidify on the substrate. Okay, so these are the steps which are happening when the pulse, okay, continuous pulses of laser get incident on the surface of the target. Okay, and you can see the entire time, okay, to generate this plasma plume is just 30 nanosecond. So in just a very small span of time, okay, immediately there is a formation of a plasma plume, and this plasma plume is get generated, okay, when you started to bombard the surface of the target with the laser pulses. This is the photograph, okay, where you can try to visualize, okay, you can try to imagine how this system looks like. So you can see there are two photographs. On left hand side you can see the photograph without a laser source, where you can see there is a big table. On that table you can see there is a chamber is mounted, okay, and the arrangement is done in such a way that you can insert, okay, a laser pulse through a window. Okay, so you can see a circle which is shown in the blue color, okay, from where the laser pulse can go inside the chamber. Okay, and all this arrangement is done. So you can see the this gate valve is there. Okay, you can see some box, okay, which is kept on the table. Okay, and you can decide the number of pulses, okay, pulse width, okay, the frequency. Okay, so all these parameters you are able to set with this box, and that box is connected to the source of laser. Okay, so you can on the laser machine, and once the laser is made on, okay, then you can control it with the help of the controller. Okay, so that you can decide how many number of pulses you want to use, 5,000 pulses, 10,000 pulses, 15,000 pulses, okay, or what is the frequency range you want to use for this laser pulse. What is the energy? For energy, what you have to do, you can control the energy of the laser, okay, with the help of the sensor. Okay, so you can detect how much energy is coming inside. Okay, if you want low energy, then accordingly you can adjust the energy of the laser. Okay, so all these parameters are important, okay, when you are trying to use this machine. On the right hand side photograph, you can see that the orange colored big box, which is kept on a heavy wooden table. Okay, so you can see that long box is nothing but the source of laser. Okay, this is the source of the laser. Okay, so the pulses of laser can start to come out from this front side of the box. Then with this single source of laser, okay, you are able to use multiple chambers. Okay, so you can see in this photo there are two chambers, okay, which is one which is exactly front of that laser, and one which is a side away, okay, of that table, okay, of the laser source. So for that you need a reflector, okay, so that you can reflect the laser pulse and just change its direction towards that chamber. Okay, once you adjust that, then you are able to use a single laser source with different chambers, PLD chambers. Okay, so these what are the parameters which affect the deposition during pulse laser deposition technique. Okay, so these are the parameters. Number one is the substrate temperature. Okay, whether the substrate is at room temperature or intermediate temperature or high temperature, it will affect the deposition of that thin film. Second is the laser pulse width. Okay, so you have to use a laser pulse width which is about 20 nanosecond, because 20 nanosecond is the lowest pulse which is available with this source. Laser pulse energy, as I said, you can also adjust the energy. If you want a high deposition rate, then you have to definitely increase the laser energy. Okay, if you want a slow deposition rate, then in that case you can minimize the laser energy. Number 4 is pulse repetition rate. Okay, that is a frequency. So in this case you can give 10 hertz, 20 hertz. Okay, so that is, you can optimize, okay, at which frequency I will get a good quality of thin film. Okay, accordingly you can use the pulse repetition rate, that is the frequency of the pulses. Number 5 is the deposition pressure. Okay, so of course we have to use a vacuum here. Okay, the vacuum is required for physical vapor deposition technique, because there is some distance from the target and substrate, and we need a very high mean free path for our target materials. So if there is a lot of noise in between, okay, then there is a lot of scattering will happen with this target material which has evaporated in the form of a vapor. Okay, and then it will not be able to reach to the substrate. Okay, so that we need optimum deposition pressure. Then the deposition time. Okay, so if you increase number of pulses, then it will take longer time for deposition. If you decrease the number of pulses, then it will take less time for the deposition. Number 7 is a gaseous present during deposition. Now, as I said, if you are depositing some metals with this pulse laser deposition, then you need not to use the oxygen, but most of the time, okay, the materials, metal oxides are basically used for this pulse laser deposition technique. Okay, and so you are able to supply some sort of oxygen there. Okay, in order to minimize the oxygen vacancies. Okay, because the laser is continuously bombarding on the substrate, the rate of the nucleation and growth in this pulse laser deposition technique is very high. Okay, so the material didn't get enough time, okay, to get completely get a defect free. Okay, so in order to minimize these oxygen vacancies, okay, sometimes is better to supply some flow of oxygen. Okay, so what are the advantages of PLD? It is flexible with all materials. Okay, for example, metals you are able to deposit, semiconductors, yes, you can deposit, insulators, yes, you can deposit. Okay, so you take this class of materials like metal, semiconductor, insulator, you are able to deposit with pulse laser deposition technique. But if you want to deposit polymers or bio materials, then this system is not suitable for that kind of materials. Second is growth in controlled gas environment. So this is an advantage. Okay, you can control the flow of oxygen, you can control the pressure. Okay, and so that you can grow the material, okay, in a constant controlled gas environment. Number 3 is very important. Exact transfer of thin films of complex material composition. Okay, so what does it mean is that, so you can see in this material which looks very complex. Okay, for example, yttrium, barium 2, copper 3, oxygen 7. So this is a very complex metal oxides. Okay, this is a very complex materials composition. Okay, so if you have the target, okay, if your target contains this kind of composition, okay, then the biggest advantage of PLD is that with optimized oxygen pressure, okay, you will get exact similar composition in your thin film. Okay, by the way, this kind of complex materials have been used, okay, in superconductivity applications, and for superconductivity applications most of the techniques fail to produce a very high quality thin film with complex material compositions. So in this area of superconductivity technique, basically pulse laser deposition plays an important role. Next point is epitaxial growth at low temperature. Okay, epitaxial means almost like a single crystalline. Epitaxial means, okay, epitaxial means, so suppose if your substrate is single crystalline, okay, let us say SrTiO3, this is the name of the substrate. Suppose you have a single crystal of SiTiO3 as a substrate, okay, and suppose you try to deposit, okay, calcium TiO3 on this kind of material, okay, then you will find that you will also have calcium TiO3 single crystalline thin film. You will also have a single crystalline thin film of calcium TiO3 on SrTiO3 substrate. Okay, so this is called as an epitaxial growth. If your substrate is highly single crystalline, then your thin film which is deposited by pulse laser deposition will also have that kind of characteristics. If your substrate is amorphous or polycrystalline, then your thin film will also be most of the times is polycrystalline. Okay, so unless and until you are not using single crystals, you will not get epitaxial growth of thin films. The last point is greater control on growth of multilayers. So as I said, because with one source of laser, okay, just by changing the mechanically changing the position of the targets, you are able to deposit the thin films with number of multi layers. Okay, so you can make a thin film with number of multi layers. What are the disadvantages of PLD? The first disadvantage is uneven coverage on large substrate area. Okay, you can imagine in this why this problem is there, because the laser pulse, okay, has a small area. Okay, because it is a laser pulse, and the pulse basically has a small area which is get bombarded on the surface of the target. Okay, so the plasma plume which is generated also has small area. Okay, so as the plasma plume has a small area, after a particular area of the substrate, you will get the gradient of the thin film. Gradient means you will get thin film with different thicknesses as you are moving from center of the substrate to end of the substrate. So at the center of the substrate, the thickness will be high. As you are approaching to the edge of the substrate, then the thickness goes down. So this is called as a thin gradient in the thin film, thickness gradient in the thin film. So for this is the biggest disadvantage, that after a particular size you are not able to deposit the thin films in a larger area. Second point is density of defects are sensitive to growth parameters. Okay, defects means, as I said, this is a very fast process for nucleation and growth, so it doesn't get enough time Okay, in if you want an epitaxial growth, then you need a very slow deposition rate. Okay, so any technique which is making thin films with very high rate, it means there are a lot of defects. Okay, where there are a lot of dislocations are there. Okay, and how it is sensitive to growth parameter, then as I said that if your material contains a very complex composition, like as I said yttrium, barium 2, copper 3, O7, in that case it is possible that sometimes if you don't supply oxygen, then the oxygen will present in the case of 6 or in the case of 5, so it may become oxygen deficient. Okay, so in that case you will write O5 plus delta. Okay, so that plus delta means something which is still remain to complete the oxygen vacancies. Third point is laser is hazardous and hence need special precautions. Okay, so if you want to use the pulse laser deposition technique, okay, in some institute or wherever you want to use it, you have to take care of this laser irradiation. Okay, radiations. So the laser radiations are dangerous to human skin. Okay, so what you have to do, okay, or even your eyes. Okay, so this is what you have to do. You have to use some sort of safety, okay, precautions, okay, so that that laser pulses are not going to harm you. Okay, and that entire room is better to indicate that from the outside of the door, you have to indicate that the laser is on inside, and you have to take the safety precautions, like you have to wear the goggles, you should have a proper proper goggles which will not allow the lasers to go directly inside your eyes. Okay, so normal goggle is not enough if you are using that goggle during the deposition technique. So you need some sort of safety precaution. You have to use some sort of safety precautions, okay, in order to keep yourself safe. The last is the reproducibility is higher sensitivity to each parameter. So if you make a thin film, next time if you slightly change some parameter, okay, which parameter we have already discussed these parameters in the last slide. So if you change any one of the parameter, then this time you will get different microstructure, you will get different composition. So it's a reproducibility is highly sensitive to the deposition parameters. Okay, so okay, we will stop here. So this complete lecture has given you an idea that how you can use the pulse laser deposition, okay, for making a thin films. Okay, for making the thin films. Okay, use particularly with the category which is called as a pulse laser deposition technique, and it comes under physical vapor deposition technique. Okay, so thank you very much.